Hello, I'm Jonathan Lorraine, presenting our work, Amortized Text-to-3D Object Synthesis, or ATT3D. 3D content creation is important because it allows for more immersive and engaging experiences in industries like entertainment, education, and marketing. However, design is challenging due to technical complexity of the 3D modeling software and the artistic skills required. Text-to-3D generative tools have the potential to democratize 3D content creation by relieving these limitations. Recent work like DreamFusion, Magic 3D, and Score Jacobian chaining synthesize high-quality 3D objects, but require a lengthy optimization for each prompt. The current design process, overviewed in the video, isn't perfect. Users repeatedly iterate between engineering text prompts and other design parameters, then rendering the results in text-to-3D pipelines. Waiting for 15 or more minutes of optimization on each design iteration creates a sporadic and time-consuming process for the user, while being expensive for the pipeline operator. We make the text-to-3D pipeline real-time by optimizing a single amortized model on many prompts. In the first stage, we train a mapping network offline from text prompts to NURFs representing 3D objects. Once trained, given an unseen prompt, we can generate the NURF in less than a second, allowing users a real-time design loop. Our method has benefits of generalizing to unseen prompts for real-time design, reducing the total training time to achieve a prescribed quality on a set of text prompts, interpolating between prompts to create a continuum of novel assets or simple animations, and amortizing over information other than text prompts, like the type of loss function, allowing new ways for users to guide creation in real time. First, how to use our approach. We want to generate 3D objects from text. We use Neural Radiance Fields, or NURFs, to represent our objects, an instant NGP backbone for representing our spatially oriented features. We want a separate object output for each text prompt, so we modulate the parameters of our network via the text. Specifically, we use a hypernetwork inputting the text embedding to modulate the instant NGP parameters. Now let's overview our training. We use the SDS loss from DreamFusion on a set of text prompts. More explicitly, each loss evaluation in our batches involves first sampling a text prompt and associated embedding, which we cache. Then we compute a modulation with the text embedding using our mapping network. As in other text-to-3D papers, we then sample the camera position, augment the text prompt with the position, sample if we're doing a textureless or shadeless render, then perform the render, which involves creating an array for each pixel in the frame, along which multiple points are sampled. Then we compute the point encodings with the modulation for the text prompt, which we calculate into the radiance, which we composite into a frame, which we add noise to, which we denoise with our diffusion model. Then we backpropagate so the rendered frame is close to the denoised frame according to the SDS loss. Now that we've seen how to use and train our method, let's cover the benefits. Amortized optimization allows us to reduce training compute time on a set of text prompts by optimizing one model on various prompts. On the right, we show a single model training with our method on all 27 prompts from the DreamFusion paper. Per prompt optimization, as in DreamFusion, uses a separate model for each prompt. We use this as our baseline and compare results. Amortization in blue allows a higher quality than single prompt training in red, measured by R probability for almost all compute budgets. We also qualitatively compare the results and find amortization performs strongly. We scale our method to the extended set of 411 text prompts from DreamFusion using an identical model size and compute budget. We show a qualitative comparison on the overlap with the prior 27 prompt training, offering similar performance. Amortized optimization reuses components across prompts, which can help explain compute savings or even allow generalization. So let's see if we have any generalization in this setup. First, we look at generalizing to interpolated embeddings. Specifically, we give our model an unseen prompt embedding, which is a linear combination of two other prompts. This produces suboptimal but promising results, which we later improve by amortizing over sampled interpolants. Next, we offer compositional generalization, which means we take two observed prompts, like a chimpanzee or a tiger eating an ice cream, then create a new unseen prompt, like a chimpanzee eating an ice cream. This works remarkably well, especially given the diverse and small set of training texts, motivating further experiments on compositional prompt datasets. To further test generalization, we use a compositional set of pig prompts with different themes in each column and activities in each row. Amortization allows generalization to unseen testing prompts with no additional training, which we show along the diagonal in red. There's no testing protocol for per prompt optimization, so we show a random initialization to align compute budgets between methods. We display the quality against compute budget for a split of seen and unseen prompts with our method in blue and green, and the per prompt optimization baseline in red. We train on the seen prompt split and evaluate at each compute budget 0 shot on unseen prompts. Notably, for any compute budget, we achieve a higher quality on both the seen and unseen prompts. We have growing benefits for larger compositional prompt sets. On the left, we show the 27 prompts from the main DreamFusion paper. In the middle, we show results in the 64 compositional pig prompts. Per prompt optimization cannot 0-shot generalize to unseen prompts, so we report a random initialization baseline. The cheap testing performance is comparable to the expensive per prompt method, shown by the dashed blue line being near the solid red line. On the right, we show results on the larger set of 2,400 compositional animal prompts with varying prompt proportions for training. The generalization is small when training on 50% of the prompts, shown by the blue lines being close together. Further, the cheap testing performance is better than the expensive per prompt method, even when training on only 12.5% of the prompts, shown by the dashed green lines being higher than the red lines. Here are some qualitative results on the larger animal prompt runs, with the same prompts in each grid. On the left, we show the expensive per prompt method, while on the right too, we show the cheap amortized methods on unseen testing prompts. Notably, when training only 50% or 12.5% of the data, the unseen prompts, which cost no optimization, perform stronger than the per prompt method, which must optimize on the data. Additionally, amortized optimization may create objects matching the text prompts more consistently, helping to explain our superior quantitative performance. Here we show the compositional pigs for the holding a blue balloon rows. On the top, we show the amortized optimization, which always creates a blue balloon. And on the bottom, we show the per prompt optimization, which often fails to generate the blue balloon, instead often just making the background blue or outright failing. Even the holdout, untrained, and inexpensive testing pig from the amortization better reflects the text than the expensive complete training run used for the per prompt pig. The model appears to share information to remove artifacts. We want to be able to take our initial results on unseen prompts and fine-tune them to higher qualities. To test this, we take a second high-resolution fine-tuning stage from Magic 3D and use it with an initialization from the amortized model. Amortization recovers the correct balloon, which we can fine-tune using Magic 3D's second stage. Per prompt optimization fails to recover the blue balloon for a pig wearing medieval armor holding a blue balloon, which we cannot fix with fine-tuning. We can rapidly fine-tune our model and target prompts. Here we show fine-tuning the prior amortized model on the left versus per prompt optimization from scratch on the right. Our method allows the model to output objects for interpolated text embeddings, unlike per prompt optimization. We synthesize a continuum of novel objects by interpolating between embeddings. Here we trained on 3 prompts: snowy rock, jagged rock, and mossy rock, which we show at the edges, then zero-shot generalized to interpolated embeddings, which produce reasonable midpoints. Some prompts produce suitable zero-shot interpolants like rocks. However, we want to improve the other prompt interpolants. For example, the object has no eyes at the midpoint between the baby and adult dragon. Can we augment our training to also sample interpolants over to amortize to improve quality? Here, we amortize over various types of interpolants between embeddings. On the top, we show the results for interpolating from a hamburger to a pineapple when sampling interpolated embeddings during training. Alternatively, on the bottom, we train with a loss that is interpolated between the 2 prompts, producing more semantically meaningful midpoints. On the right-hand side top, we show results for zero-shot generalizing to the interpolants, i.e. no interpolants used in training, which can naively dissolve between endpoints. We contrast this with training on interpolants between prompt guidance weights, the loss function, or the embeddings. Here, we show results by amortizing over the loss weights for sets of prompts. We can have creatures aging, like from a baby dragon to an adult dragon, or objects degrading, like a red convertible to a completely destroyed car, or novel terrain, like transitioning from a mossy rock to a jagged rock, or varied buildings, and different types of clothing, or more. Using interpolation, a user could quickly scrub through results, making their object more damaged or styled in arbitrary ways before proceeding to fine-tuning. We use longer chains of prompts for more sophisticated animations, like seasonality in a tree, going from a tree in the spring, to a tree in the summer, to a tree in the fall, to a tree in the winter. Or we can use arbitrary sequences of frames in longer animations. To push this out, we'll need to create a large corpus of text prompts to train our model. So far, we've only worked in the thousands regime. We may need architectural improvements to scale capacity because we often encounter a sensitivity to the prompts and hyperparameters. Further, current metrics either don't correlate with quality, like SDS loss, or are often too crude to be useful, like R probability. So, we still largely rely on qualitative inspection to assess models. Designing better quantitative metrics will help us to accelerate development and automatically identify issues like Janus faces in our assets. So, we've presented a method for amortized optimization of text-to-3D models called ATT3D. Our method first trains a single amortized model offline on various text prompts, which can then be used quickly on unseen prompts. This provides the benefits of real-time asset generation via generalizing, creating continuums of novel assets and simplistic animations via interpolations. We further allow other axes for user guidance by amortizing over other information. We also reduce the total training costs on a set of text prompts. We believe this provides a promising avenue towards general and fast text-to-3D generation. Thanks for watching. Check out our paper or our project webpage for more details.